Hello everybody to today's lecture series. Networking, research and international travel are three fundamental pillars of every of our institute. Therefore today we don't present a single institute, but Professor Bimber helped us to attract an international PhD student to present his research. Thank you.
Okay, thank you, Werner. Yeah, I think while you're still setting up things here, it's my pleasure to introduce to you Ben Jarvis. He is a PhD student from EPFL in Lausanne doing robotics, and I think that topic, especially in the field of robotics for machine learning, is probably something that you could be interested in. That's why normally this would be a talk in our lab talk series, but we just do it together with you to share basically the presentation with you. Just an organizational hint for those students that are in our seminar, we have a separate attendant list over here, but I have only one copy. So after the talks, my students or our students should come here to sign the attendance list when you're here physically. So just let me quickly introduce to you Ben. Ben is a PhD student at EPFL, so this is obviously one of the most famous technical universities in Europe, together with the most prestige technical universities in Europe, together with ETH Zurich and other technical universities, TU Munich and so on. He's in the Intelligent Systems Lab, which does robotics in various fields, and he is interested in swarms. So he's going to talk about embodied telecooperation, enabling intuitive control of complex robots. That's the title of the presentation. Ben is from Tasmania originally. He studied in Sydney, then did also a bit research at NASA before going to EPFL, where he works on basically swarms, flying swarms, and that kind of user interaction interfaces that you need for flying swarms. And with that, I would hand over to you, Ben.
Sweet. Thanks, Oliver. All right. Hi, everyone. Yeah, so I'm Ben. I think that was a pretty good summary of kind of what I've done in the past. I came from Australia. I thought Europe was kind of cool, liked the mountains, so I moved to Switzerland. Yeah, so I'm going to talk about embodied teleoperation. So teleoperation is basically when a human's controlling a robot. So we're all pretty familiar with, say, if you're flying a drone, you'll probably be holding a controller. The drone might have a camera, and you can see out of that camera. So that's teleoperation. It's a really easy way, intuitive way to fly a drone. What I'll kind of talk about are the alternatives to that, which are kind of being looked at in research as ways to make more intuitive connection with the robot, so that you can have naive users flying something with no or very little practice beforehand. Before I get into that though, all right, yeah, I just wanted to talk a little bit about my lab. So I'm at the Laboratory of Intelligent Systems at EPFL, directed by Professor Dario Floriano. I think our lab's kind of cool. We do a lot of really diverse stuff, so I just think it's kind of cool to highlight, especially because I think it kind of shows how broad robotics can be. So my background was actually in aerospace. Now I'm doing robotics research focusing on humans. So yeah, it's really, robotics is a pretty broad field, and a lot of previous skills that you learn can apply really well to robotics. So I just thought maybe kind of a cool way to show off some of the stuff in our lab. This is actually our t-shirt design that we made last year, and just features some of the robots that we use in the lab. So we have a pretty big mix of some people who are like purely hardware people, they just build robots all day. And then other people that are purely on learning or software, looking at how to control all these really cool robots. So I just thought I'd kind of show off a few of them. So kind of the biggest theme we have in the lab are avian-inspired robots. So we look at basically the capabilities that birds have, where they're able to fly in all these really dynamic scenarios. They can fly slow, they can fly really fast, they can fly around trees, they can also perch up onto branches, and they can also fly in really high winds. Things that a traditional fixed wing is not really able to do, or things that a quad-rotor drone that can do these things isn't anywhere as efficient if they wanted to fly for long distances. So we had a previous PhD built this robot, and now this has kind of led into a few other people that have been using it. So one of those, Valentin, he recently published this work in Nature Communications. So he was basically looking at, we have this drone with all these degrees of freedom, so the wings can fold and unfold, you can twist the whole wings, and then also the tail, it can spread out and it can pitch up and down, as well as yawing. And he wanted to look at how birds do their perching maneuvers. And what roboticists do when they try to optimize something like this is, so they'll look at optimizing for efficiency, or how fast can we get to the perching maneuver. Instead, what Valley did here was he looked at some studies of real birds that were similar in aerodynamic characteristics to our drone, and found that there was a hypothesis that what they're actually doing is minimizing their time at stall. So the time when they're at really high angles of attack, which is when things start to get unstable. And so he basically built a controller to test that hypothesis. And basically that's what he was trying to optimize as he did this perching maneuver. And what they found was actually that they really almost exactly mirrored the same trajectories that birds make. So that was just something really cool, where we basically have these people building these avian-inspired robots, and then someone will do software, and then we're trying to look at these links between the robots we have today and what nature's doing. And what we basically do is look at how we can use that to improve our robots. So as Oliver mentioned, I work on swarms. Specifically, I work on the human side of swarms. So robots are super cool. I also think humans are kind of interesting. But I have a colleague who disagrees and just thinks robots are amazing. So he's working on high-speed motion planning for swarms. So basically, when you have a swarm of robots, or in this case, aerial drones, and you want them to move through an environment quickly, and you don't want them to collide with each other, you want them to be able to efficiently pass through gaps, and also have them sharing knowledge between them, so they're not going to crash into each other, and they can safely find paths together. We also have a big Russian guy called Yegor who works on making dexterous catheters. So catheters that are used in cardiac surgery, basically when you have cardiac arrhythmia, where you have like a heart that's not beating normally, you basically put in this, his nickname for them are medical noodles, but basically a catheter inside the heart, and then you're basically applying small electric shocks to kind of scar the heart and return it to beating normally. So this basically looks at a lot of principles of soft robotics. So you can see this is magnetically controlled, and he's able to adjust how stiff or hard it is. So when you're basically doing the surgery, you want it to be quite rigid, but when you're navigating through the heart, you want it to be really soft, so you're not damaging anything you don't want to damage. And then another part of the lab, we actually have edible robotics. So this is kind of, I think, a really fun area of research. Basically looking at almost what's robotics going to look like in 2050. Say if you have people stranded on an island, at the moment you could send a drone to go drop food for them, and kind of the creative idea is what if they just eat the drone. So it's a collaboration with a few unis, but we're looking at basically how do we make different components of robotics edible. So Bogan here, he had this edible circular frame. You can see, obviously, a lot of this is not edible. No one's trying to hide that. But he made these edible actuators. You can just see in the bottom left that that's how this robot's actually rolling. They're basically these sacks that fill up with fluid and make it roll along. And that's all edible. Then we also have someone who's working on edible logic gates. So obviously here, there's batteries and circuits. Someone's actually looking at, rather than using electricity, can we have a fluid equivalent of that? This is stuff that you're probably not going to see in the next 3 years or in the next 10, but maybe in the next 20 years, this is something that we could see. So yeah, that's a bit of a summary of the lab. Yeah, I think it's a pretty cool summary of how broad robotics can be and a lot of the really creative research that's going on. But onto this presentation. So as I mentioned, I think humans are kind of cool. There's basically, so I mentioned I came from aerospace. Now I'm looking at how humans control swarms, and it kind of touches on themes of like cognitive neuroscience, which I don't really want to go into details of, but at least wanted to give kind of a broad overview of some of the main concepts that you look at when you're looking at this kind of embodied teleoperation. So immersiveness, presence, and embodiment, they're kind of words that get thrown around a lot, so I also just wanted to define those at the start. So immersiveness is basically an objective measure of how much you're able to engage someone's senses when they're interacting with the system. Obviously in this presentation I'm talking about teleoperation, but this is also stuff that gets used a lot in, say, virtual reality, but can also extend to, say, movies, even reading books. And immersiveness is objective measures. You look at specs like fields of view, display resolutions, types of audio feedback, and it's basically the ability to engage your body senses. And having high levels of immersiveness allows you to create senses of presence and embodiment in your users. And these are subjective senses, which are then a lot harder for people to quantify. They often come down to doing questionnaires, but ways to actually measure these explicitly is basically its whole own research area. But presence is, I guess, colloquially known as like the sense of being there. So presence is something that you can have in movies and books. If you really associate with characters or environments, you can imagine yourself there. Same thing in teleoperation of robots, where if you have, say, a really seamless visual pass-through, that can almost become indistinguishable, and you can process the environment really well. And then that goes on to embodiment, which is, I guess, the title of this presentation. So embodiment can be broken down into three definitions of a sense of ownership, so control over the thing you're embodying, sense of agency. That's basically this, ownership is the sense that you own it, agency is the sense of control, and then self-localization, which is quite similar to presence, and it's basically feeling like you're in the same space as that thing. So it's a bit of a weird concept, but basically if I'd ask you about your body, you'd probably say, most of you, that you have 2 legs, 2 arms, torso, and head. Looking at embodiment is basically the idea that that's actually malleable, that we can start to play with that your body isn't just your physical body. So there's a lot of really cool research that looks at how we can kind of mess with that, look at playful ways to kind of have people have out-of-body experiences or associate with something else. Perhaps the most famous example is the rubber hand illusion. So just before this plays, basically you have someone sitting at a desk, they have both their hands out, and then you put a board in between one of their hands. So they can't see this hand, and then you basically have a rubber hand here that they can see, and then you apply some sort of haptic stimulus at the same time to both the rubber hand and their real hand. So what you'll see when I play this video is that there's someone with 2 paintbrushes, and they're brushing someone's fingers at the same time as they brush the rubber hand. And the person can only see the rubber hand, but they're feeling the brushing on their own fingers. So it creates this really strong link where you basically feel something, it matches what you see, so you start to associate. And then you can see you can kind of play with that, where then if someone came in with a unexpected action, in this case stabbing the hand, it causes the person to flinch, even though their hand's a long way from the actual rubber hand. So they're not actually flinching because they think their real hand is going to get hit. They know it's the rubber hand that's getting hit, and they flinch anyway. So that's maybe an extreme example, but that's kind of what embodiment is. It's being able to project your sense of body into different objects. And they can be things like rubber hands that mimic your real hand, or it could be something that's not anthropomorphic, like, say, a drone. So I am a roboticist, so I want to look at how can we actually use this really cool feature to control robots. So this is something that my lab's explored a bit, and Matteo, a previous PhD student, he did a really kind of intuitive way of doing this. He looked at the rubber hand illusion, which is really famous, really well understood, and he went, all right, so if I want to control the drone, may as well just make my hand the drone. So he basically got a glove, added these markers that you can see. They're basically called motion capture markers. So in that room, there's a lot of cameras spread out, and they can track these markers really accurately, like to sub-millimeter level. So then you know really well how the hand is oriented. And then he also added some haptic motors in the hand so that he could provide some feedback. And this allowed him to do this really cool control of the drone where he's able to just move it around and the drone follows his position. So it makes a lot of sense. You obviously play a little bit with tuning how far your hand goes versus how far the drone goes, but then you're able to make this really intuitive control of the drone. And so he did a few tests. Obviously, we need to actually quantify how good things are. So he got participants, and he got them to fly through this obstacle course. So they did it both in simulation in the top and on hardware. This is something you'll see kind of in a lot of the research I show, is that typically you do a lot of detailed analysis in simulation because you can control everything. But then anyone that works with hardware knows that things go wrong often. So if you're trying to do experiments with humans, you kind of don't want to put too much weight on hardware experiments because it can be hard to justify or hard to guarantee that you have consistent conditions between different participants. So he basically had this obstacle course in both simulation and in hardware, and he'd get people to fly through these 6 gates using that same hand control. And then, as you tend to do in all this research, you compare to the classical interface, which is normally like a just standard drone controller or something like a joystick. And the main thing he found here, this was over testing 5 runs. So R1 is first run with remote controller, W5 is 5th run with the hand. It's called W because this was without haptics, so purely just the person moving their hand. And what he found was that someone with a remote controller will learn a lot quicker, and some other studies have shown that if you give people a long time to train, then using a remote control, you do get really good. People that, like if you look at drone racing, no one's using their hand, they're using a controller. Because if you spend hundreds of hours, at least current state of research, it seems like that's the best way to get like top level performance. But what he found here is that if you don't give people that training, and if you just take naive users and give them both interfaces and get them to fly, the people that use his hand controller were actually able to perform a lot better. And that's kind of the goal of a lot of this research, is it's saying, what if you have someone who isn't able to spend tens of hours or hundreds of hours training to get good at controlling this robot, and you just want them to be able to control it straight away. And so that's something that he found with this research. So this was in simulation, and in hardware, this was, again, kind of the issue with things not being quite as controllable. You often get like larger standard deviations or also just less variance between your different conditions. So here, he didn't really find much difference. But then one of the interesting parts of this glove was he wanted to look at adding the haptic feedback. So he added vibro actuators, so basically just small motors that will vibrate, and he added them at 6 different positions. So he had forward, left, back, up, down, right. And he had distance sensors on the drone. So then you're able to fly the drone, and based on how close the drone is to an obstacle, it's able to feed that back to the person's hand through haptics. And obviously first you need to test that people can actually figure out which of these is vibrating. So they did a test, they found everyone was able to do that. So then they got them to do a similar experiment, but this time, if the video plays. All right, sorry, we don't have the video, But you can see here he has walls set up, and they would just demonstrate that you're able to get quite close to the wall, and then the haptic glove starts vibrating, and then they go the opposite direction. So then when they repeated the experiment, they found that basically people with haptics would perform a lot better than people without. And this is quite a simple implementation. It's just a one-dimensional sensor fed back to one motor. It's really simple, like one line of math, but it made a huge difference. So reduced collisions by 50% in people. And this was especially noticeable in simulation because they had featureless environments. So environments where you don't have much visual texture or you don't have much context of scale, it's really useful to add these different sensors because then you're able to get more information about basically where you are in the environment. And obviously, people tended to prefer it a lot. So this is kind of a similar scenario that you follow in all this research. You look at task performance, and then you also have surveys at the end where you ask people what did they prefer, why did they prefer it, and then you can get specific about if you're trying to look at how tiring something is, you might ask questions like that. But in this case, it's not the most interesting scenario because there's a drone right in front of you. You can see the drone. You can see your hand. So can we make it first-person view? Obviously, one of the points of teleoperation is that you want to be able to explore environments. So how do we look at creating this sense of embodiment in a way that we have first-person view so we can go out and explore something new and not just control a robot in the same environment we're already in? So this was some research that the lab published in the Proceedings of the National Academy of Science, so quite a cool journal, where basically they looked at adding a head-mounted display to people and then a lot of sensors on their body. So they also had motion capture again, so they could track your limb motion and basically reconstruct after the experiment how people's upper body was, whether they were leaning, whether they had bent their elbows, shoulder joints. And then they also looked at, say, muscle activation to see if people start tensing their torsos or if they're using shoulder muscles. And then what they would actually do for this experiment is you would sit down wearing all this sensor gear, wearing a headset, and you would watch a randomized but controlled scenario of a fixed-wing vehicle that would fly and do a series of maneuvers. And they would just instruct people to do what you would do if you were controlling this thing. So you're watching it, you'll see a fixed wing, it'll like pitch up, it'll pitch down, it'll roll right, roll left, and they just instructed people to imagine that you're controlling it, do what feels like an intuitive maneuver. And in this, they found that there were two main strategies that people would use. All of them would use their torso. So that was really intuitive. I guess if you're sitting down, flying a fixed wing, and it pitches up, you're probably going to lean back. And that's what they found with everyone except these two outliers that I'll show. And then the main difference between these two strategies was some people would just keep their arms out like this. I guess when you're flying, this is really intuitive. You put your arms out, you feel like a bird. Whereas some people would actually start using their hands in this motion. So when they would pitch down, they'd tuck their hands in to go faster. When they'd pitch back, they'd put their hands out. And they did this with a few different people. And you can see this is just someone who adopted, this was the most popular strategy. And it's quite cool that without prompting, a lot of people ended up doing the same thing, which was just having your arms out and you move your torso. Then there were the people who would couple their arms as well. So this to me doesn't feel that intuitive, but I think it looks a bit awkward. But a fair few people did it. And you can see here the rolling is quite interesting. You don't tend to just turn or just lean your torso. It tends to be a combination of both. And that's something that I'll kind of get back to later. And then, as is always in the case with human research, you end up with outliers, which I'm now learning is a huge headache when you're doing research and you see someone doing something like this, because you're not allowed to tell them not to. You're not really allowed to interfere, so you just kind of watch it and accept that there's people like that. So then what they did with all this was they had all these participants and they basically trained a controller based on this research. So in this case, it was quite simple. They were just mapping directly like torso motion to pitch of the drone you're controlling. And then people were able to fly in simulation in this environment you can see here, where they had a series of waypoints. They had an arrow just to help them have a sense of direction, and then they were trying to hit all those waypoints. And then it's quite easy to have error metrics based on, say, how fast they completed it, or how close they're hitting those waypoints. And so here they also compared to this really cool simulator we have in the lab called the Birdly. It's made by a company in Zurich. I'll get back to that at the end of the presentation. But basically they compared that interface of using your torso with the Birdly simulator and then also with a standard remote control. And they found that basically people that were using their torso without the arms, so they'd have their arms out like this, they wouldn't move their arms at all. They performed really well. The Birdly performed amazing, but that's also a super expensive device, basically tailor-made for this and not that accessible or portable. But they found that they got quite similar performance. You can see this one on the left, just using people bending their torsos. And then they also found that they did testing over multiple days and found that people retained their the torso control quite well. So that was something where you can see variance over using the joysticks was quite high over multiple days, whereas it seemed like if people came back a week later, they wouldn't have degraded basically in their ability to control with their torso. And then, of course, they had to try and do it again with a real quadrotor. This is just kind of what everyone has at the end of these papers, just to show that what we've made is actually possible in real life. It's not just something that is like a video game. They're really cool. They add a lot to papers, but they often take more time than everything else. So this is cool, but we wanted to look at, can we control different robots, and especially different types of robots? So not just, say, a fixed wing and a quadrotor, but something completely different. So like a manipulator. So here we looked at basically these 3 different types of robots with different degrees of freedom. So a fixed wing that had control of roll, pitch, and speed, a quadrotor, and then the manipulator. The manipulator, you're basically just controlling the end effector, which is the bit with the gripper. So you're not worrying about all the different joints in that arm. You basically just control the position and angle of the end of it. And here we followed the same experiment or similar experiment protocol where you would sit down with the body tracking and a head-mounted display, and you would watch a view, something like this with the arrows, and you would basically just mimic whatever you wanted to do. So people aren't given prompts of, say, suggesting that torso is a good way to control it. You leave people completely free to do whatever feels natural to them. So this is an example, just reconstructing from one of the participants' body motion as they were controlling the fixed wing. And you can see at the start there's that kind of initial bit where they just get some sense of what they're actually controlling. So you don't just give them a heads-up view and they need to figure it out. And you can see that there's just this series of discrete maneuvers, and then the person does what they feel. And obviously there's a bit of lag with the person seeing something and then reacting. So this is something that you need to account for later. So when we did that across the 4 different robots, we found quite distinct patterns. So we tested the fixed wing with and without speed control and found that basically when you add speed control, it might be a bit hard to see, but when you add speed control, people start using their arms and basically tilting them to control the speed. Whereas if you just have pitch and roll, people basically only use their torsos. With the quadrotor, it became more natural to use your hands as well. And then with the manipulator, people would basically just use their hands. So some would use both hands, but a lot of people would just use a single hand. And this is where you kind of see the right-hand bias, where it might be hard to make out, but basically the right-hand bars got used more because we have more right-handed people. So basically, we did this study, looked at, okay, before we go further, are people actually behaving differently with different robots? So given we confirmed that, now we basically need to figure out, all right, we have this data, how do we use this to actually control the robots? And the way we were doing this was looking at motion synergies. So humans typically, we don't just move one joint at a time. If we're walking, we have a combination of, say, ankle, knee, and hip joints. Same as if we reach for something. You start to move your fingers before they've reached the object. So basically, we want to look at how we could capture these. And this was by using principal component analysis. You might be familiar from other fields, but basically it's a way of compressing information. So basically, over the experiment, we would get people to see first the pitch, then the roll, then the yaw. That would be randomized, obviously. And then we would get basically these discrete behaviors. We would see what they did when the robot was pitching, what they did when it was rolling. And then we're able to separate those out over here and see that, all right, when it's pitching, they would normally control the pitch of their torso. When it's rolling, they would normally control the roll of their torso. And here, when there was thrust, they would be controlling the angles of their arms. So, after we extract all that, the motion synergies, the way to actually get to the control is good old-fashioned linear regression. We tested some different regression models, but found that actually, when you have a human in the loop like this, linear regression works really well because you're not just trying to maximize a regression score. You have a human at the other end of it who's going to be using the system, and linear regression is actually really intuitive for them. They're able to kind of follow the trend and react to it. So basically, first we use PCA. We separate all the body kinematics into these three, in this case three, motion synergies, and then we perform regression on those actual motion synergies. And the idea is that people aren't just doing, say, purely pitch at one point and then purely roll. That when you're actually going to be flying the robot, you're going to be doing some combination of the two. And then something we found was that in the same way we used principal component analysis basically to compress the information and avoid overfitting, we want to do a similar thing of, in a lot of this human research, it's about avoiding overfitting. There's a lot of information with all our kinematics, and so we don't want people to have to replicate exactly the same maneuvers that they did during training as when they're controlling. So we actually found that by filtering out some of the lesser used, at least in terms of angle, lesser used kinematics, people actually performed a lot better. So when you pitch forward, you might shrug your shoulders a bit as well, but you're not really doing it consciously. So sometimes you might do it, sometimes you might not. And we found that if we filtered that out, people would tend to perform a lot better. So this then allowed them to actually control robots. So in this case, someone had control over thrust, which is why they're using hands a lot. So when there's a short distance between the adjacent hoops, they would tend to slow down so that they were able to line up better with the hoop that they're trying to pass through. It's not COVID. So we did this for all 3 robots. For the first 2, you had to pass through the gaps. And then for the last one, you were basically doing a peg and hold task. And we found that for the fixed wings and the manipulator, the proposed algorithm actually was outperforming classical components, so a joystick. Whereas for the quadrator, it was about similar. And this could be due to people having more experience with the types of controllers they use with a joystick. So that's information that you always capture at the end of a survey, basically. How many hours do you play video games? How many hours have you flown quadrotors, other robots? It's all kind of information that you capture, and then you look at the end to see if there's any correlation. And then again, we demonstrated this all on real robots. So here's someone using basically the full method to control a quadrator. It might be a little bit hard to see, but the quadrator's down here. Here we have the first-person view, which is what the pilot sees, and then this is their motion. So you can see they're able to control altitude through their pitch. So they can go over obstacles, under. He's able to control speed so that he slows down as he approaches this gap, is able to line up and then pass through. But these last 2 methods that I've shown have all used motion capture. So all these big cameras around the corners of the room, very expensive, very accurate, not very portable. So we wanted to look at, if we actually need to use this out in a field, how can you make it portable? So Corinne, a previous PhD, basically developed a thing called the FlyJacket. And it's a wearable alternative to having this motion capture suit. She put a lot of effort into making sure that it can fit 98% of the population. So, which is obviously a huge spread. You look at how much our bodies vary. And a big part of this device was they looked at the previous experiment I showed where people were controlling the fixed wing and they'd have their arms out like this. And something they were often reporting is that they had tired arms at the end of the experiment. So what they wanted to look at was having this passive arm support, where you essentially have weightless arms when you're like this. But you want to do that without controlling the person so that they're forced to have their arms in a certain condition, or so that they lose some range of motion. So a lot of effort went into basically having this passive arm support. Here it was based on a gas spring, but then there were different methods that looked at cable actuation, basically how to have weightless arms. Unfortunately, I haven't got to try it, but I would really like to. So once you develop this, they would do similar experiments. You could see that people would bend their torso back to go up, forward to go down. And like I mentioned before, there's a combination of twist and roll when you want the drone to roll. Also, this here, they're actually flying around a digital twin of EPFL, which was quite cool. So then they did a study basically testing these 4 conditions, which is people using the FlyJacket with and without arm support. And they also instructed some people to keep their arms out and some to just relax their arms. And then again, the classic compared to a remote control. And so what they found that was basically the FlyJacket, especially with the arm support, is consistent with a remote control. But there tended to be much less variance. So with remote control, you get some people that are amazing and some people that really struggle with it. And one of the big advantages of these kind of embodied devices is that they're intuitive. So you get a smaller spread of performance between people. So they did 2 tests. The previous one was basically flying above buildings. You had a lot of space to maneuver. And then they did one going between the buildings. And they found basically they just wanted to stress people more. So that they had to fly a lot better to actually complete the obstacle course. And here they found the big difference of if people didn't use their arms, they were a lot worse. So if you're just flying simply, you don't need your arms. But once you start to be more dynamic, you actually fly a lot better if you're using your arms. And with and without support didn't have a huge difference in terms of flight performance, but had a big difference at the end if you asked people if their arms were tired. It was pretty clear that people that held their arms out like this for 10 minutes, they didn't enjoy it. And then it was really interesting. They had a question at the end of this study of, did you feel physical discomfort? And I think the hypothesis is that it will be similar to this question, where people with having to hold their arms out, maybe they start to get shoulder cramps. What they actually found was that people that were using the remote control had significantly more physical discomfort than all the other methods that were wearing the FlyJacket. And they think that what this actually came down to was people getting motion sickness. So basically our visual system is really coupled to how we move. When you turn your head or your body, what you see changes. And when people were using the remote control, they were no longer moving their body, they were sitting stationary, but what they would see would change. So people were getting motion sick a lot faster. Motion sickness is something that's really hard to avoid with VR headsets. We tend to all get it at some point, but it basically comes down to the more natural you're able to make the engagement, the less motion sick you get. So the more feedback you're able to provide people, the more you're able to get them to use different parts of their body. And then again, demonstrate it on a real robot at the end. So here they were just flying a quadrotor, again around EPFL, and they also added a glove so they could identify points of interest. So now, just to kind of, as we're getting to the end of the presentation, I wanted to talk more about swarms, which, as Oliver mentioned, is what I'm working on. So first, just to clear up kind of what people's expectations of swarms are, because whenever you really talk about swarms, people think of the really cool light shows that you see, like from the Olympics. This is not it. So these are really cool. I think the world record was broken a few weeks ago. Basically, they have a bunch of computers on the ground. They've done a lot of math beforehand, and they've figured out where different robots should fly at different times. So super impressive, but not really what we're looking at with swarms. What we're aiming for is more something like bird flocks. So bird flocks, obviously, they don't have some secret communication between each other. All the birds tend to just follow their closest neighbors. So there's been some really cool studies. They found, looking at flocks outside Rome like this, that basically starlings will just follow between their 6 or 7 closest neighbors. And just by following those neighbors, they're able to make these really cool patterns, which also have some kind of a form of collective intelligence. So if you have, say, a predator attacking one side of the swarm, the other side is able to react faster than if it was just a single bird. So this is kind of the goal of swarms and what we're looking at. Currently, the state of the art is this group in China, at least as far as having distributed swarms, which means you don't have a central computer, you have individual robots making their own decisions, kind of similar to birds. So they had this really cool video to go along with their really cool research of basically this swarm passing through a forest here. So you can see there, like one drone just braked to let another go in front of it. They're able to weave between the trees. It's this really cool kind of quite futuristic scenario. And so basically what we want to look at is, all right, what if you have one person controlling this? What do they see and what do they actually control? So it could be a range of missions, like there they were tracking one person, but there's a few different ways you could do. That's basically what I'm trying to figure out in my PhD. I'm not at the end of my PhD yet, so I don't have the answer. But what we kind of did in the first year was we wanted to just get an idea of how different perspectives in a swarm make people behave differently. So we did this experiment of basically getting someone to sit at a computer with a standard remote control and getting them to control the swarm in a simplified manner. So basically all the members of the swarm will avoid obstacles and avoid their neighbors themselves, and the human is just kind of guiding the whole thing. So it's almost just like you're pushing a cloud, you're telling it to go left, right. You can also get it to spread out or contract, but all the individual motion is handled autonomously. So we would then get people to fly through an obstacle course that had these different obstacles, a forest where basically you would have all the drones kind of finding their own way through, a gap where you would have to shrink the swarm to pass through, and then a diamond at the end where you'd have to kind of expand, and the idea was that you split the swarm in two. So we'll get people to fly through that, we track all the information, and then we're able to reconstruct it. And one thing we looked at was eye tracking. So we would give people different interfaces, and then we would see what information they were looking at as they flew through the obstacle course. So we did this study with 30 people, and we gave them a range of different interfaces. So there was one group that would just see the view from one drone at a time. So they would just say, if they're doing the experiment, they might always see the drone that's furthest in the front of the swarm. And then as they move and turn around, if a different drone is furthest to the front, they would switch their view to that one. So that would all happen autonomously. And then also if, say, a drone crashed, then the view would drop from that drone and go to the one that's, say, next furthest in front. We also looked at giving people multiple screens at once. So in the scenario here, we have, say this is forefront, which means you get 4 views and the front view is dominant. So the front drone is the one with the big view, and then along the bottom you had the drone furthest to the left, back and right. And this was basically to see if people start using all the information available to them. You can think almost like mirrors in a car. And then we didn't expect it to perform well, but also just wanted to test giving people all 9 at once, see if they end up just like security guard in front of a wall of screens. And then as a control, we did a third-person view. This is basically something that's done quite a lot in literature, but is almost a bit more impractical in the real world, because part of the benefit of a swarm is that they're redundant. If one drops out, there's another drone there to take its place. Whereas if you have this third-person view, you basically have this kind of central important key drone that you don't want anything to happen to. But we figured it was important to include. So then we have a range of metrics, classic task performance, looking at how well people navigate the obstacle course, how many crashes, how well they can follow the path. I mentioned we also had eye tracking, so we can look at how much people shift their attention between different views and when they do it. And then we also have the classic surveys at the end. So one of the main takeaways was that people would really prefer views from the back of the swarm, and also that they really hated having all 9 at once. That was pretty intuitive. Turned out 9 is just way too much information. People kind of don't care about it, and they relaxed a lot more when they're at the back of the swarm compared to if they were, say, at the front or the left or the right. So the NASA TLX survey is quite a well-used survey, basically for measuring task load, so like how demanding a task was. So we looked at mental demand, found that unsurprisingly, if you give people 9 screens at once, they find it really demanding, they kind of switch off a bit. Then we would also look at, say, all the single views as well. Frustration was similar things, but we would find that views at the back of the swarm were less frustrating. So people tend to be more relaxed, and this is something that I'll get to later as well. And then we also looked at temporal demand, so basically how much time pressure you felt. This is something where the instructions didn't change at all between people, but we found that when you're at the back of the swarm, you felt significantly less time pressure. So this was a really interesting finding. Basically, people in all scenarios were told that they had to optimize for how fast, how safe, and how evenly they got a distribution on that last timed obstacle. But they tended to feel less time pressure when they went at the back of the swarm, even though they were also flying a lot slower. So this is something that we actually found agreed with some other research in swarms, which is basically that when people are trying to keep track of multiple robots at once, your sense of time actually starts to slow down. So you might be familiar with the flow state, which is something people experience in, say, some extreme sports, where basically when you have a task difficulty that's kind of matching your capabilities, you get into this kind of flow state where your time perception starts to change. And so this is where it's kind of hypothesis, but it seems like a similar sort of thing starts to happen when you're flying a swarm and you see either a lot of robots or very few robots. So when we looked at the number of surviving drones, it was also similar behavior where the views from the back would tend to have a lot less crashes, whereas views from the front would have significantly more crashes. So this was basically when you're in the front, all the drones are behind you, people would just forget about them, assume that they're fine, they just kind of go straight through the obstacle course and have more crashes. And then unsurprisingly, when you're at the back of the swarm, you are able to follow the path a lot more accurately. So when we looked at eye tracking, we found that basically over a whole test, we would track the gaze at, I think it was 8 times a second, basically where people were looking on the screen. And then we could plot over the whole thing whether they were looking mainly at one of the segments or at the others. And you can see that here in the forefront and the foreback, people spend above 90% of their time just looking at the big screen. And then when we had the 9 view, so this is all 9, people tend to kind of just like look in the middle. There's all this other information, but it's too hard to process, it's too hard to jump between them, so you just look straight ahead. So then you can see how that varied over a whole flight. And basically, when you give people all this extra information, they're not using it. They just look at the biggest thing or the thing right in front of them. So we wanted to look at whether that changes during a flight. Say, when you come up to an obstacle course, does that change and you start to actually look around? So we computed the basically visual inequality, where if it's low, it means you're looking at multiple views at once, or in a small time window. If it's high, it means you're just looking at one. So basically here, when it's a flat line at the top, it means someone was just looking at a single view. When it drops, it means they look at others. And this is kind of what we hypothesized, is that we would see people start to use the other views as they approach the different obstacles. But when we average that across everyone, turns out no. It was pretty constant the whole time. So now going forward, that's kind of the goal of what we're doing next is, all right, if you just give people this kind of boring interface of a 2D screen, turns out they're not really going to use all this information. They just look at one view because most of the time that's all you need. So the goal of my PhD is kind of how do we get people to maximize the use of information? So there's all this information in the swarm. How can we make it really intuitive so that people can start to use that in an easy way? And so that's kind of where we come full circle back to the embodiment, where the goal is now, say, instead of just controlling with a transmitter, we bring in the body control. So we try and create this really intuitive link with a swarm, and then see if people can start to use all those different views at once. And then kind of the fun note at the end is kind of our side question is, do humans flock like birds? So I mentioned we have this really cool birdly simulator. They basically get sold to arcades, and people use it as kind of just a game. We ended up with one in the lab. I don't know how, but we have it. So when I started my PhD, my professor kind of told me, go and do something with this, go do science. So what we did was I worked with a student and we made this bird flock simulation. So you can kind of ignore the background, it's kind of deliberately boring to stop people looking at it. But we got a new headset with eye tracking and we get people to fly in a flock of birds. And we basically track which birds you look at. So this is basically because a lot of swarm research came out from people studying bird flocks, and there's a lot of research about how birds actually flock, which birds they pay attention to, and we have this cool setup where we want to see what humans do in the same scenario. So we get people to fly around in a bird flock, and we see which birds they pay attention to. Is it always the one right in front of them, or do they kind of switch between others? And do the people that look at one fly better than the people that look at others? That's kind of the main thing we want to explore, just because it's a really interesting question and it's something that we're able to do. But then we're also going to see at the end of, all right, my main research is about how one human can control a whole swarm, and here we're kind of looking at what if you're just one member of the swarm, and we kind of want to see if there's some way to combine those two, where you can get people to, say, jump between control of the whole thing and control of the individual. Cool. That's all. Thanks.
Yeah, thank you very much, Ben. Very, very interesting. Do you have any questions? Anyone? Yeah.
Sorry. Have you tried, like, I noticed from cars sometimes they have like cameras around, and when you kind of park, like you get a top-down view of the car, and it's kind of easier to get all that information in. Have you tried something like that with the drones?
Yeah. Really good example, actually. So the ways cars do that is through image stitching. Basically, you have a series of fixed cameras at points on the car, and then you're able to stitch all those images together. And then they just add the actual view of the car is just a 3D model that they just add afterwards. So I am trying to do a similar thing at the moment. The difficulty is that in the car you have those cameras are at fixed points that you know really well and they never change. So you basically do the math once and that's it. Then you just apply it every time you use it. Whereas with a swarm, you don't know the positions between all the different cameras and they're actually changing. So we need to compute that basically at a speed that's fast enough that a human can actually make sense of it. So yeah, yes, it's something super interesting. It's what we're working on at the moment.
And also, like, kind of a similar question, have you also, like, do you only work on vision-based or also, like, auditive, like, maybe you can hear, okay, I'm kind of close to that. Okay.
Yeah, so that as well. I'm supervising a student who from EPFL but is doing his master's at MIT, and we're basically doing a collaboration on exactly that. So if you're doing this embodiment of a swarm, what's the haptic and what's the audio feedback? Because there's kind of a trade-off of you want to be sensing the information around you, like when you get close to obstacles, but you also want to sense if the swarm's getting too close to each other. And then also you want to communicate if there's a crash, you can communicate that to a person.
Okay. Thank you very much.
Cool.
Okay, any more questions?
So you talked about that it is easier for people with no experience to use the not the haptic, but the more intuitive controls than the remote controller. Do you know anything about when it comes to people with more experience, if they are trained longer on both methods? Does it also outperform remote controls?
So as far as I know, no.
Okay.
If it's a short amount of time, yes, but I think I don't really want to put a number on it, but when you're in like the tens of hours, I think as remote controls start to outperform.
Thank you.
Yeah, so we saw some different methods of sort of controlling the different planes, drones, whatever. and I guess we could see that intuitive can be different for different people, so what's intuitive can change. Does it make sense to sort of find out, okay, what's the most intuitive for the average person, and then to sort of tell, okay, if you want to tell that person, if you want to control that drone, use this method? Or does it make more sense to sort of have research and go into the direction of every person has their own control system, and you sort of personalize the way you control the robot or whatever?
Yeah. So it hasn't really been studied. I think it's a really good idea. I think it makes a lot of sense to basically give people a prompt on how they might control it, whether that's like an initial video, just suggestions, whatever it is. Like, you might not actually have to give them a trained controller. You could let them train their controller, but just give them 1 minute of training or something. Yeah, I think that's really interesting to explore, because like the person who's doing this, I'm willing to bet they weren't able to fly it very well. And I think if you gave them a prompt of how about using your torso, they would have gone a lot better. So yeah, I think it's a trade-off. At the moment in research, people tend to just lean towards letting people do whatever they want, or constraining them exactly to follow something. Because when you kind of get between that, it gets a bit harder to get clear data, but I think it makes a lot more sense from a user point of view.
And then follow-up question, if that's okay. So because we said that the normal remote controls after some training generally outperforms the more intuitive moving your body thing. So is the whole idea of this research to just make robots more accessible to more people? Because I guess in a specialized field, if you actually want to train a person, then a normal remote control works better, right? So is the whole idea to just make it more people able to fly drones?
I think there's two main parts. So one, yes, making it more accessible to people so that it's not a high barrier to entry to fly a robot. The other is for complex scenarios. So like a swarm, if you think actually having that embodiment is going to help you do the task better, then I think it makes more sense to go with these embodied interfaces. And then also when you have like quite complex scenarios of, you can look at like legged robots. If you want to control them more precisely than just giving them forward, back, left, right, then I think it starts to make more sense to have embodied things.
Okay, thank you.
Cool.
The short answer is, how do you fly a swarm with a remote controller? Any more questions? From this row here, the drone pilot row. Anybody else? Yeah.
Thank you for the nice talk. There were many questions in Zoom. We now need to guess which.
So there's 99 plus in chat.
Yes, I have some here. I just read some random ones. Would it be possible to apply these ideas for controlling to other technologies, for example, to reinvent how cars are controlled?
Sorry. So applying kind of body-machine interfaces to change how we control existing technology?
I guess yes.
Yeah, so with the paper where we did the diverse robots, so different types of robots, one thing we actually mentioned there is that it can enable people who have disabilities. So if someone's missing an arm, then maybe they're not able to use existing controllers. Then I think these kinds of interfaces where you personalize it to the user, it's really cool that you can enable that kind of application.
Thank you. Another question was, but I guess you answered it in the second part of your talk, would it be possible to use sensors that directly detect eye muscle activity?
Detect muscle activity?
Eyes.
Eyes. Yeah, so we are doing, I guess, yeah, the eye tracking. The newer headsets also have that involved as well, so that's what we were doing with Birdly. I think it's also quite interesting from a control perspective. The eyes are basically just pieces of brain on your face, so it's really quite cool that you're getting like a clear view of where someone is thinking. It's more than just where they're looking. Yeah.
Thank you. And can you comment on how the latency affects the controls?
Yeah, latency is a huge issue. So especially when you start to have head-mounted displays, humans, that's how you get motion sick, basically. If you add in a little bit of latency, it's horrible. Like when you turn your head and then it takes a while before the vision updates. Yeah, it's really tough. That's one reason why I'm actually working with Oliver, is that they have a really good method for getting low latency video.
Thank you. And another question was, what methods were used to measure stress?
Yeah, so stress is a hard one. Basically, you can look at measuring people's heart rate, also ECGs. So, I mean, that's more advanced heart rate, but EEGs, so looking at like skin conductivity. It gets used quite a bit, but is really difficult to get kind of quality data because you need to establish people's baseline beforehand, and then it also is prone to like temperature.
Thank you very much. Another question from the beginning. How do the electrical signals interact with the materials to control the rigidity of the medical noodle? I think this was of this.
Yeah, the medical noodle. So there's basically a few different ways that they looked at. The video I showed was fiber jamming catheters. So fiber jamming is basically when you have like a tube filled with, it can be a fiber, or there's also particle jamming. I think that was actually particle jamming, which is, you can use coffee grounds, is actually what they used in that video. So basically you fill the tube with coffee grounds, and then it's quite soft, like if you have sand in something. But then if you evacuate that chamber, so suck all the air out, it suddenly gets really rigid. And all the coffee grounds aren't able to move around freely, and they kind of lock in and hold their place. Yeah.
Thank you. And the last very general question, does the work at your lab use insights from biology to develop robots?
Yes.
Thank you very much.
You're welcome. There's also Oliver.
I have a question about like we looking to people have like kind of categories to handle like how to learning these drones to moving. So if we guess like this kind of categories of people can passing their experience with each other. So if I am from category A, I can passing my learning experience with this operators with another one from the same category. So there's something like this would be possible, like.
Sorry, you're asking about could one person pass on their learning experience to another?
Yes, but like from the same category, like.
Right. So yeah, so something we need to think about when we make these studies is who does what and in what order.
Yes.
So typically, whenever I compare data, they were different groups of people. So say 10 people might use one interface, 10 would use another, and they don't share. When people do have to share things, you randomize the order.
Okay.
Thank you.
So my question was if there was an attempt of creating a virtual environment that would represent the vision of the drones so that the pilot would only see what he needs to see. So it would not require any headset or anything. It would be just simpler for any person to control.
Yeah. Yeah, so this is a discussion that we have quite a lot. Because in simulation you can do a lot. The issue is that, like all these papers, kind of at the end you demonstrate it on hardware. And
I was not meaning like the whole simulation, but the drones would create a virtual environment in real time.
Yeah, that's the issue. So like 3D reconstruction is done quite a lot with single robots, and there's a lot of research and it's going quite well. But at the moment for like a swarm, you still can't do it in real time yet. That's something where maybe in a few years that's different and the drones can reconstruct the environment, or that's not your question?
Was there like any attempt of removing all of the obstructions so there's less of the information passed on?
What do you mean, sorry, by removing the obstructions?
The obstructions that can be easily passed by the swarm, like only the environment that is needed for control of the robots.
Sure. So doing like a simplified reconstruction.
Yes.
Yeah. Yeah. So that's something that I think shows some promise. It's something that also gets shown in quite a lot of movies where they'll have just like a vectorized space. Yeah. So I think they're often called coarse reconstructions, which is when you're just doing like really coarse shapes, kind of what like Google Earth does. That I think there's a lot of promise in. I'm kind of, yeah, I think it makes a lot of sense to do coarse reconstructions where then you can project like a visual feed over it, and then the human kind of reconstructs the finer features themselves. I think that makes a lot of sense. It's something we haven't done yet.
Thank you.
Cool.
So I think we need to stop at this point because we want to go flying before sunset, swarm. Thank you very much, Ben, and actually for all of our speakers that are here, we have a little giveaway. I think that was on your wish list,
Cool.
but actually all our speakers get that.
Yeah.
So thank you very much for this really cool talk.
Awesome.
And I think it inspired you a little bit also to do your PhD after doing your bachelor's and your master's up front. So I think everybody is signed in on the attendance list, and I have the special attendance list here for our seminar students. If you're not online, but here, you have to come to me and sign. Yeah? Okay.
Thanks so much. Also, if anyone has any more questions, feel free to send me an email. It's just benjamin.jarvis@epfl.ch. Thanks.